Does that look good?
Yeah, and I see it just turned to 12:30. So I'm happy to introduce our next speaker, Daniel Gulbrandsen from University of Wisconsin-Milwaukee, who will be speaking about cubical collapses.
Thank you very much. Thank you everyone for coming, and thank you to the organizers for this opportunity. So I will speak about cubical collapses. And this work is part of my dissertation topic with my professor, advisor Craig Gilbo. Okay, so there we go. So just as a quick outline, we'll start by introducing cube complexes, and then I'll discuss what it means to be a cubical collapsing cube complexes. And then this machinery will lead to a sort of inverse sequence that we'll use to describe a compactification for these cube complexes. And if time permits, we'll discuss how this compactification relates to other well-known compactifications. So what are cube complexes? Well, essentially they're just spaces built out of cubes. And for us, for this talk, cubes will be products of the interval from -1 to 1. And here you're seeing examples of the first few dimensional cubes. Some notation that will come up. For a cube, j to the n, I put a little circle over it if I want to call attention to like the interior of that cube. Although I'm forcing it to be like the interior that you might expect by just calling it this. And for a 0-dimensional cube, its cubical interior is just the vertex itself. Okay, and then to make a cube complex, you just put these cubes together by attaching them along faces with Euclidean isometries. Without getting into too much of the details, that just means you do what you're supposed to do and you avoid doing anything too wacky. So in this image here, you're seeing an example of a cube complex. And in fact, this cube complex is what we call a cat-0 cube complex. And that just means that it satisfies these additional two properties. That is, it's a cube complex where the link of every vertex is a flag complex. And in additional to that, it's simply connected. If you recall the first condition, the link condition is in the spirit of non-positive curvature, like in Gromov. And then forcing it to be simply connected is actually going to provide us with one of the key properties we want of these cube complexes that will come up shortly. And in this image, you're seeing cube complexes that are not cat-0 cube complexes. The first one in A fails the simply connected condition, and in B, this is a 2-dimensional object, just a 2-sphere, really. And this link you're seeing here, it has a, this link is not a flag complex. This triangle is not filled in. Okay. So one of the nice things, perhaps the nicest thing about working with cat-0 cube complexes is they have these collections of codimensional 1 subspaces called hyperplanes, and they really allow you to bring combinatorics into a lot of the arguments. And so, in fact, it's this second thing I've listed out here. I can't highlight it, but hopefully you can see my mouse moving over it. This is the key property that these hyperplanes are going to provide us, that they separate the space into two components. Okay, so what is a hyperplane? Well, let me go to the next slide here. To get a hyperplane in your cube complex, you string together a bunch of mid-cubes. And the mid-cubes are just what they sound like. For this first cube all the way on the left here, you would find 2 mid-cubes. Really, you get them by restricting your coordinate, one of your coordinates to 0. And so here, let's say I pick to start with this horizontal mid-cube. I form a hyperplane by stringing together all the mid-cubes it intersects in the right way. It must intersect them in faces that are dimension 1 less than the mid-cube. And so you do this until you run out of mid-cubes. And what you get in this case, if you started with this one that I suggested, you would get this hyperplane that you're seeing in purple. Of course, it's not the only hyperplane for this cube complex, but I've just chosen to show you one here. For another example that we'll refer to often, this should be just a tessellation of the plane, a cubulation of the plane. And hyperplanes here come in sort of 2 flavors. You get these vertical hyperplanes and you'll get these horizontal hyperplanes. And just to remind you of the property we like about the hyperplanes that you can see here is that they do separate the space into two components. Okay. So the last thing about cube complexes, and then I'll move on to collapsing. I want to enumerate these sets of hyperplanes in such a way that when you list them out, the ones that are closest to the base vertex show up first in your order, or in the enumeration, as I've called it here. And so I guarantee that by requiring that this distance, this map that maps one of these hyperplanes to this taxicab distance to the base vertex, is a non-decreasing map. And to make it even more clear with a picture, this is some finite subcomplex of the plane again. And here in red, you're seeing 8 hyperplanes, but you can see that these first 4 here that I've gone ahead and numbered, 1 through 4, these ones are sort of at the closest level to the base vertex. And so what I'm saying with this enumeration is that you just have to put those first 4 in first. And it doesn't matter what order those 4 show up. I've chosen to go with this order, but as long as those come in the first group of 4, that's okay for this enumeration. And so right away, enumerating them in this way imposes restrictions on the cube complexes. In particular, they'd better be locally finite, or you might not be able to ever accomplish such an enumeration. And so what I'm saying, this construction that I'm going to give you will apply to the locally finite case, but I'm not saying that what the statements I make aren't true for the locally finite case, just that they don't plug into this program. Okay. So now moving on to cubical collapses, which really belong in the more general framework of polyhedral collapses. But since everything here is built out of cubes, I'll just give you a very specific definition for cubical collapses. And so there's a whole history here and a whole theory. You'll recall words like simple homotopy theory, examples like house with 2 rooms and the dunce hat. What you should remember for this talk is that collapsibility is a stronger property than contractibility. So if you are collapsible, then you are contractible. And the examples I just mentioned are examples where they are contractible but not collapsible. Okay, but let's go ahead and get right into the details of cubical collapses. So to do what I'll define first, an elementary collapse, you need what's called a free face, and that's really just a place you can get started. So if this picture you're seeing on the right, this first full complex, which is a 3-dimensional cube here, you would want to collapse it in such a way you need to get started somewhere, and you get started with these free faces. And what a free face is it's just a face that's a faucet of one other cube. And what that guarantees is that you'll sort of have one side of that face that has nothing on it. And you can kind of use that to begin your elementary collapses in this case. And so what is an elementary collapse? Well, you find one of these free faces that's a facet of exactly one cube, and then you just delete the interiors, these funny cubical interiors as I define them, and you delete those interiors from your space. And in the illustrations, you're seeing 2 separate examples of this, one for this 2-dimensional cube, and on the right, you're seeing it for this 3-dimensional cube, where the free faces are these sides labeled in F. Okay, I've also heard this referred to as like a paint can process, where you empty out a paint bucket or a paint can, something like this. Okay, so what does it then mean for a cube complex to be collapsible? Well, we say that a cube complex L collapses to a subcomplex K if you can string together a sum series of these elementary collapses, essentially. And what I'm just doing here, these 3 bullet points, is each of these individual D sub I, those are the steps you get if you do an elementary collapse. And if you can perform a series of elementary collapses and transform your space from L into a subcomplex K, then you say that L collapses to K. I didn't write it, it should be written, but you call the space collapsible. Oh, it's written at the bottom here. You'll then call the space collapsible if the subcomplex that you collapse to is in fact a point. Okay. Okay, so what we're going to be after in the next few slides is sort of constructing these finite subcomplexes that will allow us to show that a cat-zero cube complex is collapsible. Okay, but it's kind of tedious to have to always worry about just doing one elementary collapse at a time. If you look at some, in this case, this finite cat-zero cube complex, you'll notice that there seems to be, if you look at hyperplanes that are sort of the furthest out that you can go, you'll find that they have a side of them that contains a whole bunch of free faces. And so the thought is, well, why can't we just do all those at the same time and then hope that they can be accomplished by a series of elementary collapses? And that's exactly how it works out. Just some terminology. When a hyperplane is as far away as it can be, I call that extremal. And formally, that just means one half space, one corresponding of these components, when you take that hyperplane away, it contains no other components that you would get by deleting any other hyperplanes. So for instance, this blue hyperplane you're seeing here, this little right strip to the right of that guy is what I'm calling a half space that contains no other half spaces for any other hyperplanes. And then something that we'll exploit a lot in really getting these collapses to be well defined. We'll use the fact that these hyperplanes, they have these carrier neighborhoods. Carrier is a common thing that they're called in the literature. Really, I'm just looking at all the cubes that intersect this hyperplane, and I'm calling that a carrier neighborhood. And in fact, it has a very nice product structure. You can see it in this image. It's just this hyperplane times that interval, -1 to 1, where you would identify the hyperplane at the 0 level. Okay, and so our goal again is to do all these collapses for this carrier of this hyperplane at once. And the way we do that is with the deformation retraction that I'm calling phi. And the image is suggesting how this is done. You just, you find one of these extremal hyperplanes, you identify its carrier with this product structure, and you march all the points to the right side. I guess in this case, the left side. The side that contains the base vertex is the right side. And you march them all to that side along the product lines. That in fact defines a deformation retraction. But I want to point out just the end of this deformation retraction, in fact, gives us a retraction. And so that's what you're seeing in this image. This is the net result of performing this carrier collapse. At time 1 under this map phi, you'll have mapped this finite complex onto this finite complex. And these retractions, the little retractions these are going to be crucial to us when we define our compactification for this complex. We're going to do it with an inverse system of these. Well, I'll show you what these compacta will be. And these maps will provide the bonding maps for us. Okay, so here's a cartoon of the whole procedure. Suppose you started with this complex on the left. Now you have choices to make for which hyperplane to start with. I went ahead and ordered them this way, and let's just agree to start from 5 and walk backwards to 1. And so you can see the steps. Now what you're seeing here are the retractions, the end results of doing the individual carrier collapses. And you'll notice, this thing's in the way, that the net effect of all of those carrier collapses brings you down to the base vertex V0. Okay, so let me back up a little bit. What I want to now do is to show that these cat-zero cube complexes are contractible. I want to write them as these subcomplexes, as in the definition, so that each one collapses onto the successive compacta. And what I'm going to do is just walk this illustration backwards. That is, we'll start with the base vertex as our first compacta, and then we'll just define the next compacta as the guy that would carrier collapse onto the base vertex. And then we just continue in that sort of fashion. And so the way that those are defined is this ugly looking formula, but you don't really need to know all the details here. Just remember that you're starting with some finite complex, you're attaching a portion of the carrier for the next hyperplane to it, and you're attaching it along the correct sort of subcomplex. So back in the previous picture, if we were going from here to this complex with two squares, you're attaching a portion of this carrier to the right subcomplex, which is just this edge on the right here. And that's all that this formula is telling you. It's how do you construct a formula for constructing these compacta. And then as it turns out, these are lemmas that need to be proven that I'm not going to give you all the details for here, but it turns out that you get a compactification, or sorry, you get a compact exhaustion for your space. Each one carrier collapses onto the previous one. And as a nice additional property, each of these compactum are cat0 subcomplexes, meaning they are themselves cat0 cube complexes. And I don't know that I mentioned this, but didn't maybe nail it down. These carrier collapses can be accomplished by finitely many elementary collapses for the finite complexes. And so this compact exhaustion gives you a way of writing the cat0 cube complex and showing that it is collapsible. Okay, let me skip this. It's not necessary for the sequel. What I now want to do is take all this machinery that we've developed and use it to construct a compactification for these cat0 cube complexes. And so I'm putting it together, these compacta that you get by putting together, forming the complexes that collapse onto the subcomplex that you want. And I'm stringing them together in an inverse sequence. And now because each of the individual objects are compact, the inverse limit that we get out of this is compact. And I just want to show that that's a compactification for the space X. And so what we need for that to be true is that this space embeds inside this inverse limit space. And if you give X the weak topology, it's a delicate procedure, but it's not the worst to show that this cat0 cube complex will embed in this inverse limit. Okay, it relies heavily here on these maps R. A lot of delicacy happens with these maps R. Okay, let me take it a step further because, well, first I'll back up. This gives us a compactification, just to reiterate, but I want to take it a step further to kind of say what kind of a compactification is this? In particular, what I'm about to do is argue for you that it gives you a Z set, and that that's going to allow us to relate it to, in particular, visual boundaries of cat0 spaces. So what I'll do is I'll assemble it into this diagram where the bottom row is just the inverse sequence that we just saw, whose inverse limit is this compactification. And on the top row, I'm just putting a factor of the interval 0 to 1. I is the interval 0 to 1 here. And so as a result of that, the top row, in fact, factors the inverse limit of the top row. It factors, it's a pretty procedural thing here. And you just get the inverse limit times an interval. And so what would be nice to have is if we could find maps for the downward arrows. And if those maps were nice enough, they would give us a map from the inverse limit upstairs, this space, this product space, to the inverse limit downstairs. And if that map is nice enough, it would give us a homotopy that will show us that this is in fact a Z set, that this boundary. So what I haven't defined for you is a boundary. And by the boundary, I'm thinking the remainder space here. The space X embeds in this compactification, take the remainder space. That's what I keep calling a Z set. Sorry if that's not clear. Anyway, so defining these maps H is again a delicate procedure. I'm just going to show you how they are defined. To get started, you can't really do much since your first compacta here is a base point. So you do the only thing you can, and this vertical line is just a constant map, and the rest of them are inductively defined. And the reason you have to split the time into such funny intervals is you'll notice you start by just sitting there, by not doing anything. And that's really allowing these maps later in this diagram to do their stuff so that they catch up with you. And then once everything catches up with you, then you start moving, you hit it with this carrier collapse, this deformation retraction, and then you define it this way so that everything works out and the maps commute. And so with that, then you just define H as sort of the product of all these maps. That gives you a map from the inverse limit upstairs to the inverse limit downstairs. And the way it was defined, if you choose any time greater than 0 for this second factor here, you'll find yourself inside one of these compact subcomplexes. And so it does instantly homotope you off this, as I was calling, boundary in this compactification. So what that means is that this compactification gives you sort of the boundary has the same shape as the visual boundary. And I'll just briefly mention the last thing, that there's another striking connection with the roller boundary here. If you're familiar with it, you'll have noticed a lot of elements of what Segev has done and others have done with cat-zero cube complexes, especially as it relates to the roller boundary. And it would seem that if you restrict your attention to the vertex set here, that I would expect, I haven't written down details here, but I expect confidently I could say you would find a copy of the roller boundary sitting inside this boundary as well. Okay. Thanks for listening.
Okay, thank you, Dan. Let's all thank Dan for his talk. And does anybody have any questions? So actually, I've got a very elementary question about cube complexes for maybe the first slide. So in my work with some collaborators, I've been working with cubical complexes, but there's a little bit of extra combinatorial information about how they get glued together. So somehow they remember the order of the faces, and if you have another cube that you're gluing to it, it's not like an arbitrary simplicial complex where you can take two faces and glue them however you want. You have to glue them sort of in the right combinatorial way. So in the kind of, when you say a cube complex, I'm just curious if that includes also that kind of information, or if you really can just glue them as pure geometric objects.
So I would say that it includes, it does not include that information. You could do any of these general cube complexes, but then when you require these conditions, for a cat-zero cube complex, we'll rule out some things. There are these special complexes, maybe that's more in the spirit. I think Danny Wise works with these. I'm not sure if that's kind of what you're alluding to.
It's almost more of the cubical analog of a realization of a simplicial set. So there's that, slight underlying structure. It kind of, it secretly knows that it used to be something closer to a simplicial set or cubical set in the combinatorial sense. And so it's got to be a realization of those, and not everything you can get by just pure geometric gluing can be such a realization.
So I'll stick with, no, it doesn't carry that information.
Yeah, this is something that we do it because my collaborator told me we should use these, but I'm not entirely sure. It does turn out for things like every smooth manifold has that kind of cubulation.
I see.
And that's really what we're using it for. So now whenever someone says cube complex, I get curious what their exact definition is.
Yeah, I have also similar, for instance, is a torus. Is that a cube complex? Where you just have one square. This is something I still don't know.
Yeah, so I think in our definition, the one that we use, it isn't. I'm
I see.
Not sure about yours.
Yeah, I think for mine, it would be allowed to be a cube complex.
Any other questions?
Yeah, could you repeat how do you get the boundary and in what sense?
Sure. So I failed to write it down anywhere, but let me go to the end here. It's this slide right here. This space gives you a compactification, and then there's a way of embedding a copy of the space inside that compactification. And then you just take the remainder space, meaning you take the set complement of the image inside this compactification. And whatever you're left with, that's what I'm calling the boundary.
Okay, and how do you see it?
How do you see it? So
Yeah.
seeing it, describing just the boundary itself is another question. You really have to roll up your sleeves and look at this inverse sequence to sort of identify points. There is an alternative way of describing this process. You see, this inverse limit is a huge infinite product. In fact, it's basically a Hilbert cube. And so there's an alternative way of doing this where you just go straight to the Hilbert cube. And there you have all these coordinates to work with. And when you do it that way, if you're, for instance, there's some things that are easier to see. Like you can really see the roller boundary sitting in there. And the roller boundary has this sort of stratification. Sorry if you're not familiar with this, but it's one of the nice aspects of it, where the roller boundary has these disjoint pieces. And when you go to this other approach in the Hilbert cube, it's easier to identify those pieces in the boundary. And so this approach here is kind of nice for showing that it's a Z set, showing that it has that property. But there's other approaches where you can describe it sort of a little more carefully.
Okay, thanks.